Subscribe now.
Yeah, so in my previous tutorial, we talked about some points, of which some include discussing the concept behind the fast Fourier transform algorithm and how it differs from the direct computation of the discrete Fourier transform. And also we talked about how the FFT leads to more efficient computation, right? So let's look at something here. The basic concept of the FFT algorithm, which is the fast Fourier transform algorithm, as I said, is a computational method used to efficiently calculate the discrete Fourier transform of a sequence, right? So unlike the direct computation of the discrete Fourier transform, which has more computational complexity, of which the number of complex multiplication is n squared and the number of complex addition is n into bracket n minus 1. For the number of complex multiplication, the n, which is the n square here, the FFT reduce it to n over 2 log of 2n, right? And then for the number of complex addition, which is n minus 1, the FFT also reduce it to n log 2 of n, right? So excuse me. So the FFT achieved this efficiency by decomposing the discrete Fourier transform calculation into smaller and simpler computation through a process known as divide and conquer strategy, of which we are going to delve in deeper. So without wasting much time, let's do some bit of example to illustrate how the FFT is able to reduce the number of complex multiplication and the number of complex addition in a given computation, a given example. So assuming that we have an FFT, with the number of sample to be equal to 1024, right? So when we want to calculate the number of complex multiplication, that's the number of complex multiplication, we have n squared, which is going to give us 1048. Let's say here, let me do it here, which is going to give us 1024 squared and is equal to 1048,576. This is the number of complex multiplication. When we come to the number of complex addition, right, we are also going to get n into bracket n minus 1, which is equal to 1024 into bracket 1024 minus 1, right? Now, so when we do this, we are going to get 1024 times 1023, which will give us 1047,552, right? So going into, if we look at the fast Fourier transform, right, the fast Fourier transform is the FFT of in terms of the radius 2 FFT, right? When you look at the number of complex multiplication, we are going to get n over 2 log of 2n, right? Log to the base 2n. So basically, if n equal to 1024, we divide by 2 and we take the log 2 and then 1024, we are going to get 5120, and then when you look at the number of complex addition, which is addition here, we are going to get 1024 log to the base 2 of 1024, and that one too we are going to get 10240. So based on this, you can see that the difference is very wide, right? Reducing number of complex multiplication from 1,048,576 to 5 5,120 is really amazing, right? So as you can see, this is more efficient. And then when you look at the addition side, it also reduces it from a very huge number, right? A very huge number, which is also 1,047,552 to that of very small number here, which is 10,240, which is also very crazy number over here. So you can see that this FFT algorithm is more efficient in terms of the computation algorithm, right? And you are not going to do a lot of computation. And in terms of the fact that if you are designing this one using any hardware, the number of hardware that you are supposed to use become very small for you. It saves cost and a whole lot of stuff that you might not get when you use the normal discrete Fourier transform, the normal approach, right? So you can even proceed and calculate the number of percentage, right? The number of percentage multiplication saved, right? Multiplication saved. Look at something here. When you divide the number of addition of FFT that you calculated over the number of addition, let's say, okay, I'm doing the addition here, so let me do the addition straight away here. So here, number of complex addition, and over the number of addition in DFT, this is a very small number. When you multiply by 100, you get the percentage of very chunk number that has been computed, that has been used by the FFT, right? So if you want the percentage that has been saved in the FFT, you need to do 100 minus this particular one that you did, right? So in terms of whatever we are doing here, when you do 100, the calculation we have done minus the 1,0240 over the 1,047,552 times 100, you will get to know that we are going to get something like 99.02%. And this 99.02%, by using calculator, going to get 99.02% is the percentage being saved when you use the FFT algorithm. And then when you look at the multiplication, percentage of multiplication being saved, is also the same approach, 100 minus the number of Redis multiplication that we did, right? Number of multiplication was 500,120 over the number of that's 1,048,576 times 100. You can see that the percentage being saved is what? 99.51%. This illustrates, or this emphasizes the point that the FFT algorithm, it's much more efficient, and it's one clear difference between the DFT and then that of the FFT as well, right? So in all, I'll try to conclude this tutorial in such a way that this FFT actually is more efficient. So as I said earlier on, it uses the divide and conquer strategy, which is use divide and conquer strategy to break down the digital or the discrete Fourier transform calculation into smaller DFTs of size of n over 2, right? Where the n is the total number of samples, as we know already, in the sequence. And if it's recursively like apply this strategy and combine the result using the trade-off factor approach, which is the complete suite, the fast Fourier transform algorithm will be able to compute the discrete Fourier transform with the significantly fewer operations as compared to the direct computation, as this calculation has illustrated over here. So in my next tutorial, we are going to look into some of the algorithms which include the decimation in time algorithm and also the decimation in frequency algorithm, and know how these algorithms are being used in executing fast Fourier transform questions. So thank you for watching, and see you in my next video.